All right, are there any questions? For tomorrow's lab, we're going to be doing computer data analysis, but I have an appointment in the morning and I might be late, so let's start lab a little bit late. Say 9:30. Let's go with 9:45 for 15 minutes. To just our regular lab room because I have to talk about this. Not 9:45, so we'll be probably 15 minutes late. Let's see. Are there any questions other than that? All right, today we're going to continue with chapter 18, and that is the KSPBs. So if we have a KSPB, you know, with the sulfides, this is something we have to deal with when we're dealing with the sulfides, and that is, you know, S2 minus is a very strong base. And it's too strong to exist in water. It's unstable because it's going to be too reactive in water. And so too reactive in water. And therefore, if we have S2 minus, it's going to attack the water completely to form HS minus and OH minus. OH minus being a much weaker base, HS minus also being a base.
Does O2 minus also have a large KV?
Yes. O2 minus is too strong. You could say the exact same thing about O2 minus. It's too powerful a base to exist in water. And so if we're looking at, and I don't know why we don't do the metal oxides too, but if we were doing the metal oxides, it'd be the exact same thing. The only situation is this, when we look at the, open this, we're in chapter 18. When we open this, you know, metal sulfides are really insoluble, and the metal oxides are highly insoluble also. Shoot, I have to open up Appendix D. But opening up Appendix D takes time because internet or whatever is so slow. So let me just try. Well, the metal oxides would be in the same boat, except if you look at Appendix D, there are no metal oxides there, so you aren't going to encounter them. But it would be the exact same thing if we were dealing with metal oxides. But here, because oxide would attack water immediately to form 2 hydroxides. And therefore, the KSP equation is a little different. And so an example would be copper 2 sulfide. Copper 2 sulfide is highly insoluble. And we would form copper 2 ions in sulfide, but the sulfide is immediately going to react with water, like this, to form HS minus and OH minus. And the K for this is very large, so what we do is we just do combine. We have to do a combine for this because there's no sulfide. In fact, this is perfect for combine because the sulfide concentration is minuscule. There is a little bit of sulfide. You know, that's one of the species that's going to be present. In fact, sulfides are common. Let's see. In natural, as far as minerals go. Let's go to Visual Mintech. Visual. Actually, I need to go here. We could just take a quick look, you know, to see what the concentration of free sulfide is in a typical sulfide. And so let's go to solid phases here, infinite solid phases, and then let's find a sulfide here, like an iron. Yeah, iron sulfide, Fe. Let's go with FeS. I'm going to go with FeS. Close that. Let's run Mintech here. Oops, arithmetic resulted in an operational flow. Did I not add that? Let me try that one more time here. Or we could go to CUS. Let's see, CUS is go back to FES. All right, something's wrong with this one. So. Well, anyway, what I was trying to show is this. The free sulfide is going to be very small here. So the combined works, but normally combined this would be a KSP and this would be a KB. But what we're going to do is we're going to just combine those into what we call the KSP superscript B. KSP superscript B. So when you look at the KSP equation for CUS, it's going to look like this. It's going to have these weird components in here. And so this is the point. For sulfides, it's different. And so KSP, when we do a calculation here, the KSP is going to equal the copper 2 concentration times the HS minus concentration times the OH minus concentration. So it's a very weird equation, but it's because we're dealing with sulfides here. And so when we look, there are actually a lot of sulfides in Appendix D, so hopefully, did that come up? No, it still hasn't come up, the book. But you just take a flip through Appendix D and you'll see it yourself. I'm not going to wait for this to come out. It takes a long time. Now, sulfides are, really susceptible to changes in pH. The sulfide solubilities can be changed dramatically depending on pH of the system. And so let's look at KSP superscript B A. And so this deals with the formation of weaker bases from stronger acids and bases. And so let's take a look at this. When we look at the KSP equation for sulfides, we always have to add this water here. It's going to generate C2 plus HS minus plus OH minus. Now, obviously, hydroxide is going to be impacted by pH, the power of hydronium here. So you can see this will form 2H2O liquids. But not only will the hydroxide be attacked, we also have HS minus, which is amphoteric. HS minus can also be a base too, so hydronium can attack that. So hydronium attacks the HS minus. This is going to form H2S plus H2O liquid. Now, if we add these up, this is going to be KSP superscript B. This is going to be 1 over KW. KW is two waters producing hydroxide. This one is going to be, if you look at the reverse equation here, it's H2S plus H2O. That's acid hydrolysis. So this is 1 over the Ka for H2S. And then just add these three equations up. We're going to get CUS solid plus 2 hydroniums This is going to go to Cu2 plus H2S. Plus 2H2S. Now K for this one, which we call, this would be KSPA, superscript B. This one would be equal to the KSPB divided by the KW divided by the KA. And so we would just do normal ice calculations here. We figure out what the pH is at the beginning.
Why is only OH minus and not H2O in the second step?
In the second, because of what we're saying is how pH, acid impacts it. And so to figure out the acid impact, we look at what hydronium can react with. So hydronium can neutralize hydroxide to form water. Hydronium and hydroxide. And so it's just, how does hydronium impact this equilibrium? So it's not good. Hydronium and water, nothing. Hydronium and copper too, nothing. But hydronium, well, it's going to attack the strongest base present. What's the strongest base? Hydroxide. And so it attacks the hydroxide to form water. But also there's one more base. Once hydronium is done with the hydroxide, there's one more base to attack, and that's HS minus. We have two bases to attack here. We can also do KF2. I mean, for example, we can attack the copper 2 and try to form a complex with, let's say, for example, ammonia. That would be another way of increasing the solubility of the sulfide, attack it with ammonia or some other complexing agent like cyanide or whatever else. Those would be all bases as well. And so here we can see, what is the solubility of copper 2 sulfide at various pHs. And it turns out this. Under very acidic conditions, copper 2 sulfide can be highly soluble. If we start off with lots of hydronium to begin with, that's going to push this to the right. Under basic conditions, it becomes highly insoluble. And so one way to control the solubility of sulfides is just by adjusting the pH. The more acidic it is, the more soluble. In fact, they say do not mix sulfides with acids, because when you mix sulfides with acids, you make a toxic gas, hydrogen sulfide gas. The same thing can be said with cyanides. You don't want to mix cyanide salts with acid because you're going to make hydrogen cyanide. So you got to be careful with this. H2S being highly toxic. All right, so those are the sulfides there, and let's take a look where we are here. So sulfides are a bit tricky because of that. If we look at qualitative analysis 18.9, and we break down the scheme, this is an analysis that aims at identifying cations present in a mixture, but not their quantities. This is different than quantitative analysis. Quantitative analysis, you try to figure out what's there and in what amounts. Qualitative is just try to detect the presence or absence of these ions. Usually we just detect the presence because if you come up with a negative test result, a negative does not mean it's absent. A negative test result just means that you didn't detect it. It could be present. It could be present in very small concentrations, and therefore it is present. And so usually we just focus on the positive test and don't really focus on the negative, because those could lead to two conclusions. One, it's not there, or two, it's there but we missed it because of the concentrations. We break down the cations. Basically somebody sat there and thought this through. This whole qualitative analysis scheme, all those steps in the flow chart, somebody sat there understanding chemistry, what kind of chemistry. They understood metathesis, acid, base, and redox, and they generated this whole qualitative analysis scheme. And so the chloride group, and this is simple because the chloride group just consists of silver, lead, and mercury. The silver, lead, and mercury chlorides are all insoluble. And then we go on to the hydrogen sulfide group. Hydrogen sulfide group, this is what we call the acidic hydrogen sulfide group. And then we have the ammonium sulfide group. The ammonium sulfide group is often thought of as the basic, even though ammonium is an acid. Because you can precipitate, depending on pH, you set a certain pH, and then you precipitate certain sulfides while leaving other sulfides in solution, and then you readjust the pH. The higher the pH, basically you'll precipitate them all. And so we have the acidic sulfide group and the basic sulfide group, followed by the carbonate group and the soluble group. And this scheme has been devised so that we can precipitate these things out like this. And then, although we didn't have all these ions that's shown here, we only had 10 ions. But in a more general scheme, you know, the HCl is going to precipitate out the insoluble chlorides and metathesis reaction. And then you do the acidic H2S, 0.3 molar HCl. 0.3 molar has a pH like 0.9 or something. You know, the pH is very low. And so you do it very low. That means only the very most insoluble sulfides precipitate here, like mercury 2, lead 2, bismuth, copper 2, cadmium, arsenic, tin, antimony. These precipitates will form. Okay, then you wash and you get the solution out here. Then we want to get the rest of the sulfides. Getting the rest of the sulfides, we do it at a much higher pH. This is going to be ammonium buffer. You raise the pH, and then you precipitate out the manganese, the iron 2. The iron 3 comes out as a hydroxide because hydroxides are even more insoluble than the sulfides. So, that's more favorable in terms of precipitation. The nickel, the cobalt, the aluminum again comes out as a hydroxide rather than a sulfide because aluminum hydroxide is less. Chromium's hydroxide is less soluble than the sulfides. And the same, and the pH is high enough to precipitate those as hydroxides and these as sulfides here. And so, we separate these and then we do the subroutines here. Subroutines taking advantage of redox, metathesis, and acid-base reactions to separate and identify these. Finally, we can add some carbonate here. When we add the carbonates, we get these, magnesium, calcium, strontium, barium. These ones are hard to precipitate. So these come out here. These are all soluble sulfides. And what's left over are what we call the soluble groups, sodium, potassium, ammonium. That's what's left over.
So it becomes more soluble at low pH because of the OH minus.
It becomes less soluble. The sulfides become less soluble at low pH. A low pH means high hydronium. Oh, more soluble. Okay. Sulfides become, you're right, more soluble at low pH. Sorry to confuse you there. But more soluble at low pH because, the hydronium can attack the hydroxide and the HS minus, shifting this to the right. Basically, Le Chatelier shift right. However, at very, very low pHs, like 0.3 molar HCl, very, very low pHs, all these are soluble. Just these are insoluble. And then just raise the pH. And so when you get the group ones, like this, we did this test here, the silver, dissolve it in ammonia, complex it. Lead, we didn't have any lead, we didn't have any mercury. And so ours was the light version of the cation group 1 analysis. Lead and mercury were missing, making the analysis much easier. If lead and mercury were present, it's a little bit more tricky. Not much. Here's group 2. Group 2, we're looking at the sulfide. Sulfide is an extremely strong base and is unlikely to be the precipitating agent for the sulfide group. So let's see. This sulfide is extremely strong base. Everybody should know that. Well, anyway, this is our KSPA, but this is with lead sulfide. So this is our KSP with this. I call it KSP superscript B just so it's different. You just got to know for sulfides it's different. We got to add a water and we get HS minus and OH minus. And then we look at hydronium. What does hydronium attack? Which species? Well, for sure the hydroxide. So hydroxide gets attacked first. And then after all the hydroxides attack, then the HS minus gets attacked. So this one's out of order. Then we get KSPA, which we just did for copper. But this is for lead. Dissolving metal sulfides, react with an acid, obviously, under very acidic conditions. Metal sulfides, Well, we can try to dissolve in water. They don't dissolve much. We can dissolve in acid, but we have two types of acid. We have the mineral acids and we have the oxidizing acid. So what's the difference between a mineral acid and an oxidizing acid? Well, mineral acid is what we would have used here in the KSPA. You know, this is just a mineral acid here. And yes, the solubility is going to go up, but not a huge amount. Now, if we use an oxidizing acid, it's really going to knock the solubility out. However, there's one major problem here. If we use an oxidizing acid like this, what acid is this? This is nitric acid. Nitric acid is the, classic oxidizing acid people think of. But the problem with this is that if we use an oxidizing acid, yes, this is going to dissolve this quite well, but we replace it with this. What's this? Solid sulfur. And the solid sulfur we usually form as a whitish sulfur, which is a polymeric sulfur, which is very rubbery. And so what we do is we dissolve this and replace it with a rubbery solid. This rubbery solid sulfur, this polymeric form of sulfur, is very insoluble in everything. And so people get all mixed up. So they got to avoid using oxidizing acids in this analysis scheme, otherwise they get. And this used to happen in our old version of, because we used to do sulfides in our old qualitative. We've eliminated sulfides, which is great from the standpoint of air quality, because our lab used to smell all the time of rotten egg, toxic H2S. And so I'm kind of happy that we don't do sulfides anymore, but also you're missing a lot of chemistry, so it's a two-edged thing. Well, anyway, we get this rubbery sulfur, but we can detect copper easily if we're just looking at copper. So this is not a great way to dissolve, actually. If it didn't form the solid, it would be a great way. We could use an oxidizing acid. Oxidizing acids can have another reaction to help, boost the delta G, boost it in the favorable direction, or the E of the cell in the favorable direction. Here's the complex formation of copper. This is a hydroxo complex. This is a mean complex. You can look at the color difference here. Concentrated ammonia. This is a test for copper 2. If you have copper 2 present, you should get a blue color with the addition of concentrated ammonia. All our bottles used to be marked ammonium hydroxide like this. The ammonium hydroxide, yes, those are the species in there, but they aren't the main species. Mostly it consists of ammonium water, so they've started switching these to aqueous ammonia as ammonium hydroxide. All right, that was the final, kind of specialty topic with chapter 18. So if you have any questions about the homework or whatever else, we can go through those later. We already started on electrochemistry in lab, but we were actually pretty much through this chapter here. And so let's pick up where we kind of left off. Here's another example of a concentration cell. That is, both cells have the same oxidizer, they just have different concentrations. So you make the right side more concentrated, the left side less concentrated. So silver ion versus silver ion versus silver ion, which side wins? The one with more. So the electrons with 0.417, figure out what the concentration is. And so this is one way of determining KSP. Determining KSP, we've got to measure the silver ion concentration. If we get the silver ion concentration, then we can figure out what the iodide concentration is, and then just multiply those together to get KSP. So experimentally, we can determine KSP based on this. The cell is just used to measure the concentration. If we know the voltage and we know one of the concentrations, we can figure out the other concentration here by using the Nernst equation. And so this is the unknown. What is the concentration of the silver ion in the anode? We've got to make sure the silver ion concentration in the cathode is big. All right, for pH meters, these are different electrodes that we have. This is the silver chloride electrode here. It's actually silver chloride. And so we have all these kind of weird electrodes here, you know, mercury, mercurous chloride. And these look like this, you know, and so when you look at these electrodes, what they have in them, so makeup can be a little bit more complicated here. This mercury. These are electrodes for measuring things like pH and other stuff here. But, you know, this is a modern pH electrode, but nowadays they're looking at using silicon chips, so to make a solid state, you know, there's no solution involved, and they have a silicon chip that's treated on the surface to be sensitive to H+. And those are very, very nice electrodes because they don't require maintenance. These electrodes require maintenance because we have a membrane here. And the membrane has to be continually hydrated. And if it becomes dehydrated, it becomes a very unresponsive electrode. Oh, there's a glass electrode. This type, so it's looking at the electrode, but we aren't going to do this here. We looked at batteries. So we already went through this battery stuff. What we're going to talk about next is corrosion. Corrosion. When we think about corrosion, like rusting of iron, normally you don't think about a battery, you know, rusting of iron, but essentially that's what it is. When iron rusts, the process is a lot more complicated than we might think. Because, you know, when we think about iron rusting, we take solid iron, we have oxygen gas, and we're going to form Fe2O3, and then we balance it 2 irons, 3 oxygens. Solid, it's rust. But it turns out rusting of iron is much more complicated than this. Because if you look at this reaction, you know, tell me, does rust, okay, we don't have to look at this up here, but does rusting of iron happen faster or slower in salt water? Yeah, I mean, salt water is going to cause things to rust a lot faster, but why? I mean, you look at this reaction, salt water shouldn't have any impact on this. Does rusting of iron occur faster or slower in a high pH or low pH? You know, in acid or in neutral solutions? Well, in acid. You know? And so there's these things that we can't really explain so well unless we describe it like this. So this slide's, we shouldn't put first. We should put this slide here first. Or actually, we don't have a good slide for. This can be thought of as a voltaic cell. Voltaic cell. And don't worry about those cell potentials there because it's a little bit confused. But basically, we have some iron here, solid. It's a solid iron here. And we have an oxidizer. And the oxidizer is going to be O2. O2 gas comes in here. And the O2 gas is going to want to pull off some electrons. And so if we need some water present, you know, for this to work properly. Because here, if we take a look at this, O2 gas needs a little bit of moisture because if the iron's dry, does it really rust? And if you had dry iron? Yeah, not really. It doesn't really, I mean, so we got to have some water in there. And that is, why do we need the water? And so there's got to be some H2O here. H2O liquid somewhere. And we got to add this to this. Well, why do we need the H2O so we can form this? Otherwise we'd form oxide, and oxide is not that stable. Oxide's a powerful base, a very powerful base. And so in this case, what we'll form is, if we have the waters come along with the O2 gas, this H2O liquid, we're going to form 4 hydroxides. So those are going to be AQ. And so there's got to be some kind of surface film here. And then, you know, there's got to be 4 electrons that go here. But where do those 4 electrons come from? Those 4 electrons are going to come from another part of this. And so we're going to have 2 ions here. These 2 ions are going to give up 4 electrons to go over here. And in the process, we're going to form Fe2 plus and Fe2 plus. And so we first oxidize at iron 2, not iron 3. Now, in pure water, this happens a little bit slow. Because what's going to happen is we need a water film here. Because what typically happens is, well, iron's a conductor. So this is what we call the cathode over here, and this is what we call the anode. Now, the cathode and the anode are in the same chunk of iron. You just got one chunk of iron. But over here, the oxygen is pulling electrons, and you know where they pull electrons. The oxygen can attack anywhere, but where do things corrode first? Have you noticed, like, if there's a dent in the body panel, corrosion happens. Yeah, at the creases, or because think if there's a corner here, is this corner iron as well bonded to the rest as a surface iron? No, a corner iron has what we call higher free surface energy. And so this is a less stable iron than these. And the irons stuck in the middle are the most stable. And so if we're going to corrode, we're going to corrode at defects and steps. And so there's got to be some kind of kink here or something that causes these irons to be less well bonded than the others. And so this is how it works, because this is not necessarily where the O2 attacks. Where the O2 attacks is going to pull the electrons. Now all these irons are filling pulled electrons, so the weakest link irons are going to be the ones that are going to pop off or be oxidized. So these ones over here, which could be in a different part of the iron structure, are. And so, this iron here, corner iron, is definitely one that's easiest, most easiest to pluck. But let's say there's some kind of defect in the structure here to cause these irons to be less stable. And so maybe defect in structure. Although I didn't draw it. Anyway, this is what's going to happen. We're going to generate hydroxide at the cathode and iron 2 at the anode. But we know about space charge, because if there's no salt bridge, is this going to happen? No. No, it's not going to happen. So if we have water, this is what's going to happen. If we have water, we need moisture. If there's surface water, then we're okay. It'll happen slowly. If there's surface water, then the hydroxides are going to migrate to the anode, and the iron 2s are going to migrate to the cathode. And if that happens, if the hydroxides migrate and the iron 2s migrate, then we can neutralize the space charge. Now, if there's salt water present, that's way better, because if there's salt water present, immediately when these ions are formed, they're going to be stabilized. So for example, if we had sodium chloride present, then the sodium ions can neutralize the hydroxide charge, and the chlorides can neutralize the iron 2 charge. And therefore, corrosion is going to happen much faster in salt water, because the salt water is going to act as a salt bridge. If we don't have that salt bridge, then this reaction is going to be very, very, very slow. And so in deionized water, iron does not rust all that fast. In salt water, it's going to rust much faster. Now, which one moves faster? Now, okay, we're stuck with water, Di water. Which one moves faster, the hydroxide or the iron 2? You guys remember diffusion and diffusion rate? The diffusion rate of gases is inversely proportional to its square root of its molar mass. That's the diffusion rate. And so the more massive it is, the slower it moves. And so the hydroxide, being a lot lighter, is going to move a lot faster. It's going to have a much faster diffusion rate. In fact, if you double the mass, it's going to go. It's going to take a square root of 2 times faster. So if we have salt water, it should corrode much faster. And if we have acid, it should corrode much faster. Why acid? Well, corrosion is especially significant in an acidic solution because rather than having this reduction reaction here, O2 plus 2H2O, we have this one, O2 plus 4H plus yields 4H2O. This one has a reduction potential of 1.229 volts. This one has a reduction potential much lower because we're forming hydroxide. Is hydroxide as stable of a product as water? No, water is way more stable. And so this is going to have a much better reduction potential. So this has a higher reduction potential in acid than in water. And therefore, that's going to boost the cell potential for this. And so an acid solution, we're going to form water here. Well, that means we're going to lose the H pluses, but we still need salt, you know, because if we lose the H pluses, we have to balance out the missing cations there with some other cations. So salt water is going to effectively enhance both these in acid versus in whatever. All right, so how can you create defects? Well, you take an iron nail and you hammer it in. You just take a hammer and start hammering it in. So this is an iron nail here, but if you look at the two ends have been hammered flat. Well, if they've been hammered flat, you've screwed up the structure. You screwed up the structure and you've created a lot of defects. And so if there's going to be corrosion, where is the corrosion most likely to occur? It's most likely to occur at the sites of the defects or the corners or creases or whatever else. And so this is what you're seeing. Now they put some stuff in here so you can see what's going on. So the hammer, they put phenolphthalein in here. So they put phenolphthalein in here. Phenolphthalein turns pink in the presence of hydroxide. So you see we're generating hydroxide on this part of the structure. These are not galvanized iron nails. And so on the normal part of the iron here, it's fine. So this would be here. Let's say this is pristine iron here, crystals. So the oxygen comes and attacks it. They can't pull off the electrons here. And it's going to pull off the electrons in the defective sites, but it can generate hydroxide. And so where we see pink, this is the cathode. The oxygen comes in, pulls the electron. Where do the electrons come from? Well, this is metal, so electrons are going to come from there and there, because there and there are the weakest iron atoms, weakest held, weakest. So, and so you can see, do you see that precipitate around there? It's a green precipitate. The green precipitate is iron 2 hydroxide, which is green. You can see it here, this little precipitate here. That means the hydroxide moves rapidly. The ions barely move before they're attacked by the hydroxide and precipitated in the metathesis reaction of iron 2 hydroxide here. And so we can see the iron 2s are being generated. As they're being generated, the hydroxides are precipitating out. Okay. Here, what they did was they just took a nail and then folded it here, and they kinked it. When they kink it, they're going to introduce a lot of defects. And so now we have 3 anodes, 3 anodes and 2 cathodes here on this nail. So we can see where the sites of corrosion will be on this nail. Take a look at, we have a pristine nail here. They didn't hammer the ends of this nail. Instead, what they did was they wrapped zinc around it. If they wrap zinc around it, let's say the oxidants come in to attack the iron here. But what's easier to oxidize? Is it easier to oxidize iron or zinc? Well, it turns out it's much easier to oxidize zinc. Zinc has a higher oxidation potential than iron. And so the oxygen comes here, pulls on the electrons on iron, but ends up pulling the electrons onto zinc. Zinc's an excellent anode. And so what they do is they just wrap some zinc foil around the iron. They're in electrical contact, so that can happen. In fact, this is the whole process. The bulk of the iron is protected by a process called galvanizing. Have you heard of galvanized iron? Galvanized iron is they'll take an iron nail and dip it in molten zinc. They put a zinc coating on there. And therefore, when oxygen comes, it doesn't attack the iron, which is the structural, the mechanical part. It attacks the zinc. The zinc is what we call sacrificial anode. Sacrificial anode means that we'd much rather have zinc as the anode than iron as the anode, because the iron's what holds the building together, or whatever you nail together. And so if the zinc corrodes, the problem is once all the zinc is gone, then the iron will start to corrode. When that happens, forget it. Now, so this is what we call a galvanized nail, and the iron's going to be protected. It's going to remain pristine as long as the zinc is there, sacrificial. We don't have to use zinc. We could use anything with a higher oxidation potential than iron. And so another common sacrificial anode for iron is magnesium. Magnesium is easily oxidized compared to iron. And so magnesium is another excellent. How about copper? Is copper easily oxidized? No, copper's oxidation potential is lower than iron. And so if we tried to galvanize this using copper, it would be a big fail because look what gets corroded. Does the copper get corroded? No, the copper stays pristine, it's the iron. And so if we have copper and iron together, then well, the iron is going to be corroded. And so this is good for protecting copper, but not good for protecting iron. So protecting iron, well, you know, steel buildings are made out of iron. Cars are made out of iron. And so protecting iron is very important. And so how can we protect iron? Well, we can't coat copper on there or attach copper, but we can do zinc. Or we can just protect the iron completely by sealing it off from the environment. Problem is for example, some people try to electroplate copper on here. Copper, the reason they try to electroplate copper on here is copper provides an inert barrier to protect the iron underneath here. So, for example, the Statue of Liberty is copper-plated iron or copper-coated iron. The problem is that if there's any gap here, if there's a gap here, then here the cathode is going to be the copper and the anode will still be the iron. What we can do is we can seal off this gap. You know, rather than using copper, people use paint. If you paint this and make sure there's no gaps in the paint, then you're okay. You know, because the paint will provide an inert barrier. Problem is if there's a crack in the paint, forget it, it's going to start to rust. And be in trouble. Whereas zinc doesn't suffer from this problem. You know, galvanize, you don't have to galvanize the whole thing, you just galvanize part of it. And you got to make sure there's moisture around. But as long as that's the case, then we're good. Because if this were in air, that's a different story. And so there could be gaps here, galvanized iron. This is copper plated iron. And copper plating is not effective. Painting is fine. Here are galvanized nails. That silver coating is zinc. There. This is the idea behind a lemon battery. Have you seen those lemon batteries? Let's take a quick look at a lemon battery. Let's try to you could make a lemon battery like this. Actually, you could make it out of 2 pennies here. Anyway, this is a galvanized nail here, which is zinc. It's zinc. This is a copper penny. You can make it out of 2 pennies if you scratch the copper off. You know, if you scratch the copper off a penny, do you know what's underneath? Zinc. And so you could take 2 pennies, one with copper and the other with the copper scratch. You don't have to scratch all of it off. You just need to scratch a little bit to expose the zinc. You expose a little bit to the zinc, and this is what's going to happen. Zinc is going to be your anode or cathode? Anode. Copper is your cathode. What's the oxidizing? Zinc is your reducing agent. What's the oxidizing agent? No, copper is not the oxidizing. Copper is just to feed the electrons. The copper here is just to feed the electrons to. There's no copper 2 in lemons. If there was, it'd be blue.
Isn't the lemon acidic though?
Lemon's acidic. So what's the oxidizer?
Citric acid.
Citric acid. Acid's the oxidizer. H plus. And so H plus is the oxidizer. The copper's feeding the electrons to the H plus, and the electrons are coming from the zinc. But the H plus can attack the zinc directly, so our voltage is not going to be as high as you'd expect, because there could be both direct reaction, H plus attacks the zinc directly, and indirect reaction, H plus attacks the copper, which pulls the electrons off the zinc. We need a piece of wire.
How does the potato battery work?
Potato battery work? Let's take a look at the potato battery, see if we can figure it out. This one works pretty well. Sure. Well, here. Potato batteries, the same thing. Now, obviously, if you have an oxidizer like H+, now a potato's very acidic. Do they have a lot of citric acid in them? Not necessarily, right? I don't know what the pH of a potato is. I'm kind of curious. What is the pH of a potato? Oops. God, the pH. Good potatoes with a pH ranging from 6 to 6.5, slightly acidic. And so there's going to be a little bit of acid there. And two, it would work even without any kind of oxidizer there, because of there's going to be an equilibrium. Obviously if you have a good strong oxidizer, it's better. But there's going to be an equilibrium here between the copper and the copper 2 ion. And so even if there's no acid present there, this equilibrium still takes place. That is, some of the copper will be oxidized to copper 2. It's just a natural equilibrium. But that concentration of the copper 2 is very small. And so even if there wasn't an oxidizer in here, what we're going to do is we're going to build up a little bit of negative charge on this electrode when it sits in a potato, let's say. And then at the zinc, we have the same thing. At the zinc, we're going to have an equilibrium that's going to build up a little bit of charge. So we have two metals there. And the two metals are going to have different degrees of negative charge buildup depending, and they could just be sitting anywhere. There doesn't have to be an oxidizer. But when we look at this equilibrium here, the negative charge, which one do you think is going to build up more negative charge on the electrode itself? The copper metal or the zinc metal? Zinc, because it has a higher oxidation potential. And so what we have is an imbalance of negative charge. If we have more negative charge here, negative charge is like water. And so it's naturally going to flow over to the copper, even without an oxidizer there. And so even if that pH was 7 in a potato, it still could generate a voltage, because of the equilibrium involved with the metal electrodes. Well, look at it. There's some potatoes with a pH of 5 to 5.2. Well, 5 to 5.2 is no problem. That's acid. And that'll be a good oxidizer for your battery. Lemons are way better because lemons have so much citric acid in them. You generate a much better voltage with a lemon battery than a potato battery. 0.93 volts for potato. That's zinc and copper. I used to do the lab. I used to do the lemon battery lab. To build lemon batteries, put them in series like this, and try to generate voltage, light up LEDs. But that's when I had a lemon tree and I had lots of leftover lemons that I needed to get rid of. So. But now I don't have a lemon tree, so I haven't done the lemons. Lemons are kind of expensive. I can't do that anymore. Anyway, let's go back to this. You can buy sacrificial anodes at Home Depot. Do you know they sell sacrificial anodes at Home Depot? Magnesium for pipes, gas pipes. And so a lot of people have iron for gas pipes. And, you can buy these sacrificial anodes, magnesium, and then hook them up, prevent corrosion. Those. Basically, on a ship like this, it's already corroding. You can see lots of rust. Do you see that? Lots of rust. But here you can see big blocks of magnesium to help slow that corrosion down, protect the iron. This magnesium, that magnesium has to be in electrical contact with the iron. Here's galvanized nails, another sacrificial anode. So this is called cathodic protection or sacrificial anode. All right, so that's corrosion of iron. Now we're going to look at the last topic of chapter 19, which is electrolysis, causing non-spontaneous reactions to occur. This would be like recharging the battery. You know, if we try to reverse this reaction, what we did was we did zinc and copper 2, and then eventually the battery's going to die. Once the battery's dead, then what we can try to do is recharge it. When we recharge the battery, we try to force the reaction to reverse. So this is the reverse reaction. The reverse reaction is going to have the self-potential minus 1.1 volts. It's non-spontaneous. So if we get a power supply and force the electrons backwards, then we can recharge it. We'd need greater than 1.1 volts to do that. And so this is the power supply that we hook up here. And so with the power supply, what we want to do is this. Normally the electrons flow to this. This would be the cathode. And so if we hook up the power supply there, we're going to hook up the cathode of the power supply to the copper here and make the copper the anode. So we want to reverse the reaction. If we make this the anode, then the electrons are going to be generated here. We'll regenerate our copper too. And so the battery pulls in the electrons from the anode, and then the battery is going to force electrons over here. You know, this used to be our anode, but we want to make this the cathode. So we're going to force the electrons here and reduce the Zn2 plus back to zinc metal. And so this would be recharging the battery here by forcing the electrons to go backwards using an external power supply. Now this battery has to have a minimum of 1.1 volts. It's got to be greater than 1.1 volts actually to make this happen. And so that's electrolysis. And so point 1, a voltage significantly in excess of the calculated value may be necessary. This is called overpotential. And so we need to give it an extra kick. This has to do sometimes with the mechanism, you know, how things get reversed. Competing electrode reactions may occur. That is, when we try to reverse this, we might not get the reaction that we desire. Because what happens is this. The battery is going to oxidize the species with the highest oxidation potential. And the battery is going to reduce the species with the highest reduction potential. And that might not be what we want, or what we think. Reactants are often in non-standard states. Yeah, that's for the most time, most of our batteries. The nature of the electrodes matter. You don't have to know any of this really, except this, the overpotential, and that competing reactions might occur. In the electrolysis of molten sodium chloride with inert electrodes, only one oxidation and one reduction are possible. And so what we want to do is we want to reduce the species with the highest reduction potential and oxidize the species with the highest oxidation potential. Hopefully that's sodium and chloride. And in aqueous sodium chloride, well, there aren't any other species, because if we have inert electrodes like carbon or platinum, then, you know, basically the only thing here, let me just show you what they're talking about here. Now, this is tricky here, because in this type of electrolysis, this has got to happen in one beaker. So we have NaCl liquid. And so that means we have sodium ions and chloride ions in liquid form. There's no water here. If there's water, it could lead to trouble. Okay, over here, we're forcing electrons, so we got power here. In the power supply, you know, there's a positive and negative terminal with the power supply. But the positive terminal is pulling the electrons into it. And so the electrons are going to flow this way. Here. So if these are like platinum electrodes, then those aren't going to react. Platinum is very, very difficult to oxidize. Chloride is much easier to oxidize. And so what's going to happen at this electrode is we're going to get chloride. 2 chlorides goes to a chlorine plus 2 electrons. And those 2 electrons are going to be sucked into the power supply. So at this electrode, we're going to generate bubbles of chlorine gas. Gas is going to come up here. Over at this electrode, we're going to reduce the species with the highest reduction potential. Well, sodium versus chloride ions, sodium ions are much easier to reduce. And so over at this electrode, sodium ions are going to pick up an electron. Actually, 2 sodiums picks up 2 electrons to form 2 sodium liquids. Now this is molten sodium liquid. So molten sodium sodium liquid's less dense than sodium chloride. So sodium liquid's going to float to the top. Now you don't want molten sodium liquid coming into contact with chlorine gas, otherwise you're going to get an explosion. So we have to have a barrier here. This barrier is going to prevent mixing of sodium liquid with chlorine gas, which would lead to a very powerful redox reaction. And so this is what's happening here. Now, if we tried to do this in water, you know, the problem with this is it's going to be expensive because you have to heat this up. You have to heat this up to melt the sodium chloride. Have you ever tried melting table salt? It's not easy. You try to melt table salt, it's not easy. It costs a lot of energy. So why don't we just do this in water? If we do this in water, there's a huge problem, and that is this. If we tried to do this in aqueous sodium chloride, it's the same thing. In aqueous solution, we'll have sodium ions AQ plus chloride ions AQ. This would be NaClAQ. And then we'll just put an electrode here. You see this is one pot. You could do electrolysis in one pot because there's no spontaneous reaction here. And so we don't need two beakers. We can just do this in one beaker here. And so the power supply is pulling electrons off. Well, now we have one more species. You know, we got platinum and chloride and sodium, and we have water present as well. So we've got to account for the water. And so which species has the highest oxidation potential? Sodium ions, water, or chloride, or platinum? And so we look at the oxidation potentials here. If we look at the oxidation potentials, we've got to look at the oxidation potential for sodium ions, the oxidation potential for chloride, the oxidation potential for water, and the oxidation potential for platinum. Which one is the biggest? Still loading. Okay, it came up. Maybe we can just take a look at the oxidation potential. What species has the highest oxidation potential on the chart? No. Highest oxidation potential, easiest to oxidize. Fluorine's not easy to oxidize. Nor is fluoride. Fluoride has the lowest oxidation potential.
Oh,
Actually, you're right. We got the chart here. This will be easier. Lithium. The problem with this chart is is backwards from yours. This is a chart of oxidation potentials. In your book, you have a chart of reduction potentials, right? And so lithium has the highest oxidation potential of 3 volts. In our chart, it would be negative 3 volts, for the conjugate, lithium ion. And so, well, anyway, as far as comparing oxidation potentials, we're looking at oxidation potential of sodium ions aren't even on here. Looking at water versus chloride. It's easier to oxidize water or chloride. Yes and no. There's one thing you have to memorize, unfortunately. All right, let's start off with the species with the highest oxidation potential, which is lithium. Now, you have to read your chart backwards because lithium, this is a chart of reduction potential, so if we want the oxidation potential, we flip this backwards. If we flip it backwards, we reverse the chart. So lithium has the highest oxidation potential of plus 3 volts. And so let's just work our way down to smaller oxidation potential. Work our way down. See what we can encounter first. Do we encounter chloride or do we encounter water? Well, here's chloride here. You see? What is chloride's oxidation potential? Tell me what chloride's oxidation potential is. Yeah, negative 1.36 volts. What is water's? Water's here. Negative 1.229 volts. So which is higher? Which has a higher oxidation potential? Water. Chloride at negative 1.36 or water at negative 1.229? Chloride at negative 1.229. That has a higher oxidation potential. Oops, water. Water at negative 1.229 has a higher oxidation potential. And so what we expect to oxidize at this electrode, the battery is going to pull electrons. It doesn't care. It's going to pull the electrons from the species that's easiest to oxidize. According to our chart, water should be easier to oxidize. And so according to the chart, this should have the highest. Highest according to chart. But there's not a huge difference. I mean, there is a significant difference, but it's not a huge difference between water and chloride. I mean, this highest according to chart. But in order to oxidize water, a lot has to happen. When you oxidize water, take a look at what happens. Bonds have to be broken. The water has to be completely torn apart to form oxygen and H+. And so this is just completely destroyed in a way, the bonds and everything else. And so what that means is this. Do you know why we have to have an overpotential? Why we have to have an overpotential is sometimes it like, have you ever heard this expression, it takes money to make money? It's like, if it didn't cost anything to make money, you just got money, then that's great, But sometimes it takes money to make money. And so in nature, that's the case. In nature, this is favorable, perhaps, in certain reactions, but what happens is you have to break bonds. In order to break bonds, you have to expend a lot of energy. And you don't get that energy back immediately. You get that energy back later. And so it takes money to make money. Well, you got to invest in some energy to break the bonds in order to get the return at the end. And so what happens is this. Overall, this one makes the most money. But This one, it takes less money, because for chloride, all you have to do is pull the electron off. You don't have to tear the molecule apart, break all the bonds, do a whole bunch of other stuff. Basically, with chloride, it's just plucking the electron from the outermost shell. And so in terms of, this one is a larger investment initially, but with a bigger return. This one is a much smaller investment initially, but with a smaller return. And so what happens is this, you got a whole bunch of collisions and this other stuff happening. Even though this is the highest according to the chart, when there's competition between water and chloride, chloride wins. This is oxidized versus water. In other words, you have to memorize this, that it's because of the lower investment in energy, chloride wins, even though you don't get as much in return. And so this one, chloride wins because it costs less money to start, and therefore it's easier. In other words, water has a higher, what we can call overpotential, or a higher initial voltage needed. You might not have that initial voltage. You know, let's say you don't have much money to invest. You know, if you don't have the voltage required to invest, you aren't going to pull it, even though the return is bigger. Mm-hmm.
So if the battery is a certain strength, would oxidize water instead of chlorine?
Yeah, if the battery were very powerful, would oxidize water in the end. Initially, the chloride would become oxidized first because it's just easier. But in the end, water would be more favorable, so you'd end up with a mix. But if the battery is not very powerful at the beginning, then this chloride is going to be oxidized. No water is going to be oxidized. And so even though we should be oxidizing water to form, when we oxidize water, we form oxygen gas. We end up oxidizing chloride to form chlorine gas. And so what happens at this electrode is we form chlorine gas.
Why doesn't it form hydrogen gas?
Well, it could, but to form hydrogen gas, it can't happen at this electrode, because what's the charge on hydrogen in water? +1. Hydrogen, at this electrode, we're taking electrons, so we can't take any electrons off hydrogen. It's already lost. We've got to give electrons to hydrogen.
So, could you have water as the cathode?
Yeah, no. We could. Yes, we could have water as a cathode to form oxygen. In fact, we do this. If there's no chloride around, do you know what's oxidized? If there's no chloride around, water is oxidized. In fact, this is electrolysis of water. At one electrode, oxygen is produced. At the other electrode, hydrogen is produced. In fact, let's see over here. Over here, we want to do the reduction. What has the highest reduction potential? Well, we got water. We got sodium ions. We got chloride ions. And we got platinum. Well, platinum is very unreactive, so I'm not going to worry about that. And so what has the highest reduction potential? Water, sodium ions, or chloride? And so we go to the species with the highest reduction potential and work our way down. The species with the highest reduction potential would be fluorine. Here. Fluorine's reduction potential is plus 2.866 volts. Now let's work our way down until we see one of our species. So not yet. Here we have chlorine, but we don't have chlorine, we have chloride. So we'll work our way down. Oh, here we have sodium ions. Reduction potential of sodium ions, minus 2.714 volts. Where's water? Water appears to be at the bottom of the list. Not at the bottom of the list. Where is water? Here's water. Water has a reduction potential of minus 0.828 volts. So what has a higher reduction potential, water or sodium ions? Water. And so here, there's no tricky stuff. Water is going to be it. And so at this electrode, hydrogen gas is being produced. Hydrogen gas through the reduction of water. So we got here just two H2Os plus 2 electrons yields H2 gas plus 2 hydroxides. Okay. And so we need some kind of barrier here, because if hydrogen gas and chlorine gas came into contact, you'd have an explosion. So we need some kind of physical barrier to separate the two gases so that they don't react with one another. And so if we try to electrolyze sodium chloride in molten sodium chloride, we form sodium metal. But if we do it in water, well, water has a higher reduction potential than sodium ions, a much higher reduction potential. Therefore, water is what's reduced, not sodium ions. So we can't produce sodium ions. We can produce chlorine gas, but not sodium metal. Sure. And so let's go. And so what I was saying is whenever we have a competition between water and chloride wins. And the reason is this whole idea of overpotential. The overpotential is because of all the bonds. This overpotential is the initial investment. You know, when we're talking about overpotential, you have to have a higher voltage than what's really expected, because you have to have a high initial investment of energy to break all the bonds and stuff. And so that's what the business of overpotential is. And so we need a high overpotential for this, not just the voltage that's written here. Just skip that. All right, then we have quantitative aspects of both electrolysis and voltaic cells. This is good for both cells, not just electrolysis. Electrolysis is easier to control. So let's look at the stoichiometry of electrochemistry. When we do the stoichiometry, we need certain things like the Faraday. The Faraday is 96,485 coulombs per mole of electrons. We need to know what an amp is. You know, 1 amp is defined as 1 coulomb of charge per second. 1 coulomb of charge per second. And then we can do our stoichiometry. So a cell, you know, it could be an electrolytic cell or a voltaic cell, doesn't matter, any cell. A cell operates for, let's go 10 minutes at 560 milliamps. How many grams of copper solid, grams of copper solid will be plated after this? So we know that copper 2 plus 2 moles of electrons goes to copper solid. And so in this example, we have 10 minutes. And then we'll convert this into seconds, 60 seconds per minute. And then we'll use this amps. 560 milliamps is 0.560 amps. 0.560 amps is 0.560 coulombs per second. And so that would be 560 millicoulombs, which would be 560 milliamps. And then we know from Faraday's 96,485 coulombs of charge for every mole of electrons. And then from this, we know that there are 1 mole of copper, there's 1 mole of copper plated for every 2 moles of electrons. And then we know that copper weighs like 63.55 grams, 63.55 grams per mole. And so this is electrolytic or voltaic. It doesn't matter. You know, cells, we can measure the current. When we know the current, we know how many coulombs of charge pass. We know how many coulombs of charge pass. We know how many moles of electrons pass. We know how many moles of electrons. We can figure out how much reagent was consumed or reacted or produced in that. Okay. Here they're refining copper or purifying copper by electrolysis. Here's the electroplating. Electroplating is plating other metals on top of other metals. This is a chloralkali process for generating sodium and sodium metal and chlorine. Industrial process. They're much more sophisticated. Here they don't have to melt it. They can just do aqueous, which is cheaper. So this is a much more cost-effective way of doing this. They use liquid mercury as an electrode. Liquid mercury is not very reactive. It's hard to oxidize this stuff. That's actually the end of chapter 20. Well, actually, we knocked off a couple of chapters right there. Not chapter 20, sorry, chapter 19.
What is chapter 20 about?
Kinetics. We did lab yesterday on kinetics. Or not yesterday, when was it? Thursday. Lab Thursday. So let's take a look at kinetics, which is chapter 20. Did I already download these? Let's see. I didn't. What we're going to do in the computer lab is this. The first half of chapter 20 is just empirical analysis of data. Wow, 9 minutes, 1 minute. Alright, maybe it's going to take a long time to download the PowerPoint, so let's skip it. Although I think I put it on Piazza. Put chapter 20 on Piazza. That'll be quicker than trying to download it off here, I think. Or maybe not. Let's see how long Piazza takes. So, yeah, it's gonna take a long time to download off Piazza too. Maybe we'll just forget it. Well, anyway, if we look at reactants, let's look at a reaction. Let's say we're looking at decomposition, and that A decomposes into products. And we watch the concentration of A over time, and what's going to happen is the concentration of the reactants is going to go down versus time. So as the concentration of the reactants goes down over time, let's say we start off here, and then over time it reacts. It doesn't happen in one instant. So things start to react. And we have different patterns of reactions. So for example, it could react linearly, that is, straight line. And so what we might see is like a linear decay in the amount of product here. And so this we call constant rate of reaction. Constant rate of reaction. When it's a straight line like that. But often what happens that you see is you don't see a constant rate of reaction. What you see is something that's non-linear, that is, it's a curve. And this curve is it could react like this, where the rate starts off rapidly. So actually, maybe I better just draw it here. That is here. This would be linear or non-linear. And so it has a faster rate at the beginning, and then it kind of slows down. So it rapidly reacts, and then as the concentration decreases, just slows down. This is like hot objects cooling. Do hot objects cool linearly or non-linearly? So let's say you had a hot piece of metal. Does it cool at a constant rate, or does it cool at a non-constant rate? It cools at a non-constant rate. Hot objects cool like this. The hotter the object, the faster it cools, but as the object approaches room temperature, then the cooling rate slows down. And so, let's say I have a hot object. I have a hot piece of iron at 200 degrees. I have a hot piece of iron at 200 degrees. How long will it take to cool back down to room temperature? Now, if what's going on? If it had a linear cooling rate, then it'd be so easy. If it cooled like this, if the hot piece of iron cooled like this, then we can easily predict it, because we can easily generate the equation of this line and then say how long it's going to take to get to this temperature. Is so simple, right? Y equals mx plus b. If it cooled like this, which it does, how long will it take to hit room temperature? And so if it cools like this, and we say, okay, it's going to take how many minutes to get here, we need the math that's involved. We already know the math involved in this. It's easy.
It's different depending on the surface area, right, of the object you're talking about.
Yeah, that's going to have an impact. So let's just take one piece of iron and measure it experimentally. Well, the thing we could do this. We could just go in the lab and measure it. Just time it. How long does it take? Right? That's kind of what we did here with our reaction. We just went ahead and just measured it. But if we want to make a prediction, then we need to know the math of this. And do you know the math of this? The math of this is easy. The math of this is more difficult. When we have something that has a rate that changes, then we need not algebra. We need calculus to do it. If we know calculus, then it's easier, much easier to do something like this because we just have all the math that's required, all the mathematical equations that's required for this. But, you know, calculus is not required for this class. So what we're going to do is we're just going to take all the equations that we get from calculus and use those to make the predictions. And so if we have something that's nonlinear, it depends on how, you know, there's lots of different nonlinears out there. And so, you know, there's not just one nonlinear. So it's not just, okay, it's either linear or this. You know, because nonlinear can mean lots of different things. Here. And so each of these things will have their own set of equations, right? And so one thing is we have to recognize what kind of nonlinear it is. And then we aren't going to go crazy. We're just going to keep things as simple as possible, and we're just going to do two nonlinear scenarios. Otherwise we definitely need calculus to do this. And so we do two nonlinear scenarios, and this, so just remember which equations belong to which nonlinear scenario. Okay, now when we're talking about the rate is just the slope, you know, the delta A here over delta T here. When we look at the delta A's versus delta T's here, actually we're out of time, so we'll continue this. This is what we're doing in lab tomorrow, is we're going to try to figure out what the nonlinear is, because we got nonlinear, right?
So tomorrow's lab, you said, is going to be the computer lab?
Yeah, tomorrow's lab, but I need to talk about what we're doing in the computer lab first. So we're going to meet in our regular lab room, 162. But if you didn't catch it, I'm coming in late tomorrow, about 15 minutes or so. And so, come late tomorrow.